Hi. In this final lecture on tipping points, what I want to do is I want to talk about how we can measure tips. Now remember previously we've talked about active tips or direct tips where the variable itself causes the system to tip. And then contextual tips where something in the environment, remember in the case of the percolation model, causes the environment to suddenly be willing to tip. And we've also talked about tips within class, so from an equilibrium to an equilibrium, and tips across classes, from an equilibrium to complex. What we'd like to do is now have some sort of way of measuring how big a tip is. Like, is it a tip that was completely unexpected, or is it a tip that maybe was, sort of likely to happen? Or just how rare the event that the system tipped into was. So to do that, we need some way of measuring. Now that's a key thing in this models class, right? Is we want to be able to take these models and take them to data some way, right? To use data. So if we're going to use data, we have to have some measures. So what I want to do in this very simple lecture is just introduce two different measures on what tipping points are to measure the extent of a tip. One is going to use something called the diversity index. The other is going to use a formula called entropy, which is used a lot in physics, not that much in social science. Okay, so let's get started. Let's first think about an active tip. So in an active tip, what we have is we've got, this ball up here, and it's sitting on top of this peak, and it could either go this way or this way. And if it heads this way, it's going to go down here, or it can head down here. Each of these things has a 50% chance of occurring. Once the system is tipped, then it's either going to be to the right or to the left. So if it's down here, now there's a 100% chance that it's over here, and there's no chance it's over here on the left. When we think about a tipping point, what we can think of is that previously what was going to happen was uncertain. It could either go left or it could go right. But once the tip has occurred, we know what's happened. We know the system is now completely going to be in the right. So one way to think about tipping points, and the measure we're going to introduce, is going to depend on that idea, that the uncertainty goes away. Initially, there was some uncertainty. It could go left or right, but after the tip, we know where it's going to go. So we're going to measure tippiness by reductions in uncertainty. So to get there, we first need a measure of uncertainty. The way to think about that is we want to think about changes in outcomes. So initially, there's a whole bunch of different outcomes that could occur, but then after the system tips, either there's only one outcome that could occur, that maybe if it goes to some equilibrium, or it could be the case that there's a whole bunch of other things that could occur. So it could have gone that you thought for sure A was going to happen, but after the tip, it could be B, C, or D. So what you want to think of is changes in the likelihoods of different outcomes. So how do we measure that? How do we measure likelihoods of different outcomes? So we're going to do, as I mentioned, two measures. One is going to be this thing called the diversity index, which is used in social science a lot, in economics, political science, sociology. And the other is going to be a formula called entropy, which comes from physics and information theory. So here's the idea. Suppose we've got four outcomes, A, B, C, and D, and suppose each one has a probability of 1/4. So each one has a 1/4 probability of being true. Question is, how do we measure how unlikely that is? Here's what we're going to do. First, we're going to introduce the diversity index, and here's how it works. Suppose you've got four possibilities, A, B, C, and D. So here they are, PA, PB, PC, and PD. So remember from probability that these four things are going to have to, if those are the only things that can happen, these are going to have to sum up to 1. Well, we want some measure of sort of how diverse this distribution is over these four outcomes. Because if it's a fourth, a fourth, a fourth, a fourth, that's more diverse than if it's a half, 0, 0. So here's the idea of the diversity index. We basically first compute the probability that if two people meet, they're of the same type. So let's suppose this is a distribution across people, and there's types A, B, C, and D. Well, what are the odds that they're both type A's? Well, that would be P to A times PA. And what would be the probability they're both type B's? Well, that would be just PB times PB. And what's the probability they're both PCs? Well, again, that's PC plus times PC, and then finally they could both be Ds. I can write this in a fancy way. I can write it's a summation sign of PI, I equals A, B, C, or D, PI squared, right? So I can just take each of these types, P1, PA, PB, PC, BD, square them and just sum those up. So this little funny sign here means a summation sign. So let's suppose I have PA equals PB equals PC equals PD, so they're all 1/4. Well, then what I'm going to get is I'm going to get 1/4 squared plus 1/4 squared plus 1/4 squared plus 1/4 squared, which is 1/16 plus 1/16 plus 1/16 plus 1/16, which is 4/16, which is 1/4. So that's telling us it's sort of like 1/4. So to get the diversity index, what we do is we just take, it's equal to 1 over the summation of those PI squareds. So that's going to be 1 over 1/4. which is equal to 4. So what that's telling us is that, look, it's like there's 4 types here. Okay, so our diversity index, remember, was just 1 over the summation of these pi squareds. So before we had PA equals PB equals PC equals PD, and we got a diversity index of 4. Well, let's suppose we have PA is a half, PB is a third, and PC equals a sixth. So what we have here is we've got 3 types, A's, B's, and C's, but they're not evenly distributed. So what we'd like is our diversity index to be maybe a little bit less than 3, because this isn't quite 3 types. So let's see what happens when we get it. We're going to get PA squared, which is 1/4, plus PB squared, which is 1/9, plus PC squared, which is 1/36. So you can put all these over 36, and we get 9 plus 4 plus 1 over 36. That's 14 over 36. So 14 over 36, if we take the diversity index, that's going to be the opposite of that, which is 36 over 14. So that's 2 and 8 over 14, or 2 and 4/7. So what the diversity index tells us is, well, this is not quite 3, because you're more likely to get A than you are to get C, and so we'll call this 2 and 4/7. So what the diversity index is sort of tells you approximately how many different types of things there are. So why does this work to measure tips? Well, what we could think of is, if initially we thought there were 5 places it could go, and then after the tip there's only 1 place it could go, the diversity index would flip from 5 to 1. If initially it could go to A with probability a half, B with probability 1/3, or C with probability 1/6, then we could say, well, initially there were 2 and 4/7 places it could go, but then if it tips and goes to C, we can say now there's only 1 place it can go. And so we'd get a reduction in the diversity index from 2 and 4/7 down to 1, and that helps us measure the extent of the tip. Okay, now let's turn to entropy. Entropy is a slightly more complicated formula, but it also measures the degree of uncertainty. So entropy, again, comes from physics and information theory, and it looks like this. It's equal to minus the summation of those pi's. That looks similar to what we had before. But now times, we're going to do times the log base 2 of pi. Now what is the log base 2? Log base 2 of 2 raised to the power x just equals x. So it tells you what's the exponent of the number with respect to 2. So it tells you the power of 2. So if I take the log base 2 of 1/4, that's going to equal the log base 2 of 2 to the minus 2, right? Because I can write 1/4 as 2 to the minus 2. So that's just equal to minus 2. So if we take our example we had before and computed the entropy, we'd get minus 1/4 log base 2 of 1/4 plus 1/4 log base 2 of 1/4 plus 1/4 log base 2 of 1/4, and then we got one more, plus 1/4 log base 2 of 1/4. If you haven't done logs before, don't worry about it. I just want you to get a sense of the idea behind this, what entropy measures. So I'm going to explain conceptually what this is after we can finish this calculation. So we're going to get minus 1/4 times minus 2, right, plus 1/4 times minus 2, plus 1/4 times minus 2, plus 1/4 times minus 2, right? And we get this, remember, because the log base 2 of 1/4 is just the log base 2 of 2 to the minus 2, and so it's just minus 2. So that gives us minus, and I've got 4 times 1/4 times minus 2, so I get minus minus 2, which equals 2. Okay? So what does entropy tell us? What entropy tells us is it tells us the number of pieces of information we'd know, or the number of bits of information you'd have to know in order to identify the outcome. So let's go back to our example where there's 4 outcomes, A, B, C, and D, and they're equally likely. Well, how many pieces of information would I have to tell you in order to identify what the outcome is? Well, suppose I said, first thing I could do is I could say, well, it's either an A and B. It's either an A or B or C or D, right? So I could divide this set in half. Then, in the second thing, I could tell you whether it's A or it's B, right? So I could always identify which one it is by asking 2 questions. So question 1 could be, is it A or B or C or D? So you have to name which of these 2 sets it's in. And then question 2 would depend on question 1. And if you said it was in A or B, then it would just ask, okay, is it A? And if you said yes, then it's A. And if you said no, then it's B. So entropy tells you just how many pieces of information you would have to know to identify the outcome. And so if there's 4 outcomes, you'd only need 2. To summarize, the diversity index tells you sort of the number of types, and entropy tells you the amount of information you would need to identify the type. Right, so in our example, the diversity index was 4 because there were equally spaced 4 types, right? A, B, C, and D were all equally likely. And the entropy was 2 because with 2 questions, you could identify which the type was, right? You could ask, is it A or B or C or D? And if they said C or D, then you could say, was it D? If they said yes, it's D. If they said no, it's C. So entropy is the amount of information, diversity index is the number of types. Either one of these things will work. So let's see this in action from our first example. Remember we had initially, it was sitting up here, and there was a 50% chance it goes here, and a 50% chance it goes here. So the diversity index in this case would be 2, right? Because there's 2 outcomes, and each one is equally likely. And so if we did our formula, we'd just get 1/2 squared plus 1/2 squared, which is a fourth plus a fourth, which is equal to 1/2. And then we take 1 over 1/2, and that gives us the diversity index of 2. Now, if you compute the entropy of this, we won't do it, you're going to get the answer 1. And so why? Because all you need is one piece of information. It would say, is it to the left or is it to the right? And that'd tell you where the ball is. So diversity index is 2, entropy is 1. Well, what happens after this tips? After this tips, it goes over, let's say, the left with a probability of 100%. Well, what's going to happen to the diversity index? Well, when this thing goes to 100% and 0, then the diversity index is now 1, right? Because you know where it is. And the entropy is 0 because you don't need to be told anything. You don't need any information where the ball is because it's already on the left. So there's no uncertainty left in the system at all. So what you can see is this thing, the diversity index went from 2 to 1, entropy went from 1 to 0. That's how we can measure how much a system tipped, right? Because it's telling us it went from, we don't know what's going to happen, it can either go left or right, to now we know where it is. So the number of types has decreased from 2 to 1. Or if we think in terms of information, we can say, previously I needed 1 piece of information, now I need 0. So if you think of tipping points, when a system suddenly tips to some new thing, we go from a situation where we didn't know what was going to happen to a situation where maybe we knew what was going to happen. So that would be true if we had a between-class tip from a complex situation to an equilibrium situation. Alternatively, right, we could have a system tip from a nice equilibrium where the diversity index was low and the entropy was 0 to one that became incredibly complex where uncertainty was very high.